Alright, so we are looking at this functions frame. Okay, so we've been dealing with functions. It's kind of what we're getting into, those patterns, right? Functions are just special patterns that we've been talking about. Arithmetic, geometric, all that stuff, except we're kind of adding on to that. Okay, and so kind of the way to think about a function is it's just a pattern where if I give you a certain input, it's going to kick out an output, which we often put f of x or y. Okay. Now with these functions, with these special patterns, there's two characteristics that we want to talk about first. The first one is discrete. Okay. The way we think about discrete is it's changing in pieces. Okay, or chunks, unconnected dots. That's another way to think about it. Okay, they're unconnected dots. There's nothing going on in the middle. Okay, whereas the other one, continuous, is exactly the opposite. Okay, it's a line. We connect the dots. It's a constant change. And so all of these patterns that we're talking about can be either discrete or continuous. So it's a line, constant change. So always changing. Okay. So, kind of once again to talk about that function. This would go in here, but I can't quite write small enough. Functions are, we often call them relationships. Between an input and an output. Okay, and it's a pattern such that in a way that each input only has one output. Okay, that's kind of where we're going at with here. So we're going to talk about the two main ones this year. There's lots and lots of different types of functions. Okay, but we're going to focus on two of them, and it goes back to those special patterns, that arithmetic and geometric patterns that we were talking about. So that's what we're going to take a look at next. Okay, so this is that column on the left side. Okay, so I'm going to start off with the linear function. Okay, that arithmetic pattern, right? So we may want to down here put arithmetic. Okay, and what do we do with linear? It's adding or subtracting by the same number. Right, it's that constant difference. That's what linear is dealing with. Alright, so with linear, when we talk about our rate of change, I forgot an of, didn't I? Let's make that a different color. Rate of change. Okay, so with that, that's just the number we're adding or subtracting. Okay, that's the number we're adding or subtracting. Suppose I should put number here, huh? Number we're adding or subtracting, and we often call it the slope. Okay, it's often written as the letter m, and it's, we also write it as a fraction, that rise over run, that y, change in y over the change in x. Okay, when we're talking about slope. So, when we look at a linear function, what does it look like in the table? Well, we've got our input and our output. Okay, we have some numbers. Remember this left side, this input, that is our interval, right? We need equal intervals for this to work. Equal intervals. Okay, here we're adding 1 each time. That's how the interval is changing. Now for the f of x, the output, okay, that's where we see the pattern. So our output would look something like this. Okay, and so how is this one growing? Well, we are adding 4, or not adding, subtracting 4 each time, right? So if we're talking about that rate of change, where do we see it? We see it right here in this x and this y. It's the y over x, right? So it would be negative 4 over positive 1. So our rate of change is negative 4 when we simplify. You know, that's our slope. That's our rate of change. Okay, now let's graph this guy. So remember when we're graphing a linear, and this probably helps to remind us with the equation, right? An explicit equation in linear is that y equals mx plus b. Okay, we can also write it y equals b plus mx. Okay. Or we can even change the y's to f of x's. Okay. And we've got our slope, m, or m right there. Okay, and our b, that's our y-intercept, right? That's our y-intercept. And our y-intercept is where the input is 0. What that output is, that's our y-intercept, right? It's where we start. So we'd start at positive 3. Then our slope, we go down 4, right? Because it's negative 1, 2, 3, 4, and to the right 1 to make our next point. Go down 1, 2, 3, 4, to the right 1. Okay, as many times as we need to. Or up 4 and to the left 1. Okay, now depending on whether this was discrete or continuous, we either leave it as dots or draw the lines. For us right now, we're going to draw the lines. But notice how we can see that minus 4 and that plus 1. Same thing that we see here, right? Okay. So when we talk about our equations, our explicit, everything matches up with those same pieces. Okay, so where do we see it in our equation? Well, in the explicit, we see our starting number, our y-intercept right here, and then we see our slope with the x right there, right? That's where we see the slope. That's our starting number. Okay, that's the growth. That's where we see that rate of change in an equation. And to tell us if it's linear, it's 4 times the variable. It's that rate of change multiplied by the variable. Okay, now if you remember the recursive, if we're talking about the recursive, it's f of x equals f of x minus 1, and then we are adding or subtracting that rate. So plus m, that rate of change. And then our y-intercept shows up in the f of 0 equals 3. That's where the y-intercept is. Okay, so in our case here, right, if we're using our example, we would go f of x equals f of x minus 1 minus 4, and then f of 0 equals 3. Okay, so there's kind of some ways we can see that. Now, just to remind ourselves, how can we tell if it's linear? In a graph, it's a straight line, right? In other words, we have that constant slope. You do want to check that. Okay, in a table, how do we see it? Well, you have the equal interval, right? That plus 1 on the left side in the output, or input. And then the constant differences, or adding or subtracting the same number. The same number in the output. Okay? in an equation. If it's a recursive, we see it in the after the f of x minus 1, right? It's f of x minus 1 plus the growth. That plus right there, that's where we see it. If it's an explicit equation, which is what we look at more often, it's multiplied by the variable. Okay, the variables are multiplying. Okay, so there's the linear. Okay, there's some quick information about that linear, just reminding us about that one. So once again, there we go. Now on the right side, we're going to talk about the exponential type of function. Okay, we also call that one geometric. Okay. So, if we are looking at this one, this is when we multiply or divide by the same number. Okay, here we're talking about the constant ratio or factor. Okay, that number we're multiplying by over and over and over again. So the way we talk about this one, we really don't call it a rate of change. I mean, we can call it a rate of change. You may want to call it even a factor of change. Sometimes they will use rate, though. But its rate of change actually is not constant. The factor of change is constant. That one isn't. So that's just simply the number we multiply. Okay, and we just like with the slope, we really don't have a fancy special way of doing this one. So not much we can do about that. They never made one. So when we look at this, okay, it's not a straight line, so it's going to be curved. So let's come up with an example real quick. So we've got our input and our output, our interval, and our output. We'll do a simple one where we're multiplying by 2 each time. Notice our interval is still adding by 1. We just look for the same interval, and then we're times them by 2 each time. Okay, so that's the growth factor. Okay, that's our growth factor, that multiplying by 2. Okay, that's our common ratio, the number we're multiplying by. So if we graph this one, it would look something like this. Negative 2, 1, negative 1, 2, 0, 4, 1, 8, 2, 16. Oops, I messed up on my 1, didn't I? And 3 clear up to 32. So it keeps going this way and then shoots up. And remember, when it's going this way, it's never going to cross the x-axis unless we shift it up or down. Okay. Now, when we're talking about this one, okay, with our explicit equation, it's kind of like a slope intercept. Y equals a times b to the x, or f of x equals a times b to the x, where a is our starting number, okay, our y-intercept is a. So in our case, f of x equals 4, and then what our growth is the b, so times 2, and then it always has the variable raised to the power. Okay, we typically don't rearrange that one. We like to leave it like that. And when we're talking about the recursive, it's exactly the same setup as the linear, except instead of plus, we do times that factor. Okay, suppose we could call that a b multiplied by b. Okay, so in this case, f of 0 equals 4, and then f of x equals f of x minus 1 times 2. So when we're looking at the growth, fairly easy to see right here, right? Multiplied by 2. We see it right here because it's got the x is an exponent to it. Okay. Now, in a table, it's easy to spot because it's the number we're multiplying by. However, I think it's tough to tell when we're dealing with the graph. And so what I kind of do is want to look at that distance of the y value. Okay. If I look at the distance from the x-axis to where the y value is in the graph, I'll notice that they're getting twice as big each time, from 1 to 2 to 4 to 8 to 16 and so on. That's kind of a way that you can see it, though it's really not the best. Okay, so how do we tell in that graph? Kind of explained it, but how would we write that down? Well, it's a curve, right? Rising or falling quickly, because we do it the opposite way too. Distance from x. I won't write that. That was part of the graph. Okay, but looking at the graph, you can kind of see it too. All right, what about with the table? Pretty easy to see. The number we multiply or divide. That one's pretty easy to see. In the equation, it's the variable is an exponent, right? An exponent, and that tells us that it's going to be exponential. Okay? So, what's the point, I guess, on there? If you missed anything, you can pause it. But what's the point of having these functions called linear and exponential instead of arithmetic and geometric? Okay, well, arithmetic and geometric deal more with just the numbers, not so much with the inputs and the outputs. It's really tied to just, how we make a group of numbers grow. Okay, that sequence like that. That's more what arithmetic and geometric are. So that linear and exponential, it gives us more real-life applications, I guess, would be the main thing. If we strictly were with arithmetic and geometric, we don't have all those real-life applications, I guess, possibilities. I don't know why I put a comma there. But it gives us more real-life applications, more real-life possibilities, okay? More useful. And just, works with two variable relationships. Okay? So, there we go. That's pretty much it. I know there's a backside to it, but that's really for you guys to talk about. Just remember, if it's something continuous, it's something that you have to show grows. So, think about what kind of story problem you could do for that one. For discrete, same idea. Okay. Actually, maybe I'll give you a quick example. So, like continuous, if we were doing, let's call this the linear one. Okay, if you were doing continuous, it would have to be something that keeps, you're adding it constantly, that it works to add a little bit at a time. So a good example of that would be, filling up the bathtub. Tom, fills up the bathtub, and every minute, let's say every second, it goes up by 2 millimeters. Okay, something similar to that, where you've got something being filled up constantly, okay, in some format. What would it look like if it was discrete? Okay, well, using that same idea, I would say Tom's water faucet is broken in the bathtub, bathroom. Okay, to take a bath, he has to fill up cups in the kitchen and bring it to the bathroom, okay, to the bathtub. And so he fills up, 5 cups every minute. Okay, that would be more discreet because in between the time he pours it into the bathtub and goes back to get it, it's not growing at all. Okay, so that's kind of the difference between them. So here would be a good opportunity for you guys to create another example. Make sure your interval is equal. Make sure you're adding or subtracting. Should be a straight line somehow. And fill in this stuff, and then we can take a look at it. You can come show it to me. I can tell you if it's right or wrong. Alright, now for the exponential, same here. Create another example. Just make sure you're multiplying or dividing here. The intervals are still going to be equal. Some sort of curvature. And then your explicit recursive equation, make up a story to go along with it. But if we're talking about the exponential, okay, a continuous could be like a bank. Okay, Eliza is saving, no, not saving, invested, let's say that, invested $200, and it's compounded continuously. Okay, how much does she have in 5 years? Okay, so thinking about that one, it's would work because in the bank account, it's constantly refiguring how much more interest to add to it. Okay. Now, would something be discrete in that sense? Okay, it would be like she's still in a bank. That invested the 200, but it compounds once a month. And she doesn't get the interest until the last day of the month. So it really only compounds that last day. So if she takes it out sooner, she won't have that extra. So there's nothing happening in between the end of the month for each one. Okay, so kind of a way with the exponential, continuous, and discrete. And like I said, make your own. And there you go. There's our frame. Make sure you're using that to help you out with all the cool stuff we do.